lead exit. So a very interesting topic today. We did have a lot of people register, and we noticed that bandwidth may be a slight issue throughout the presentation thanks to GoToMeeting or GoToWebinar. So if there is a slight delay, I do apologize in advance. As always, all of the slides will be distributed to you at the end of the session, and also a full recording of the webinar. So don't worry, if you have any issues at all, you will be able to catch up later, and we'll be sharing those at some point later today or tomorrow, so you won't miss out. Today, I am joined by two colleagues, Deanna Papic, who is based in our Croatia facility. Hello, Deanna. Good afternoon.
Hello.
And also late in the evening, Lie Zhao, our colleague from our Asia Pacific business in Shanghai, China. So thank you to both of you for taking the time to share your experience on DC transformers. And today there is a slight change. Unfortunately, for our viewers out there, you have to listen to me for a little while today because I've been asked to do the introduction. So bear with me, please. I will introduce the topic today, and then I will hand over, don't worry, to our technical experts who will share with you far more insightful and deeper understanding of DC and designing for DC. If you have any questions, then we will, of course, as always, try to get to them at the end. You can click the question mark button at the top of your screen, enter a question in there. Don't worry, it won't disturb anybody. I get all your questions, and as always, I will be back at the end of the presentation to give the questions to Deanna and Leah, and we'll do our very best to answer as many of the questions as we can. So moving on from there, yes, there we go. There's the nice delay. So HVDC market overview will be me. I will then be handing over to our colleagues to go into more detail. So Deanna, let's get going, as today we have quite a long presentation, I believe. So first of all, why are we talking about DC here today, or HVDC rather? Well, of course, as probably most of you know, the hundreds of people out there, that HVDC technology is not new. It's been around for decades, if not longer. But of course, historically, it was typically used or deployed in limited applications with very specific use cases. Whereas today, growth in renewable energy generation, interconnections, long distance transmission lines, we're seeing more and more questions at Weidmann coming to question us about our experience with DC and knowledge sharing, basically. And of course, that's from both OEMs who are evaluating HVDC opportunities, so the transformer manufacturers themselves, but also the utilities as well, who are having to consider different technology, different applications for their networks. And there are many organizations out there who have experience in this, but there are also many who are strictly AC based companies. So we do see a much higher rise in questions coming to us today about how we can design for DC power. I mentioned that HVDC, next slide please, Deanna. I mentioned that HVDC technology is certainly not new. And here, please, if you are sat out there with a project and it's not on here, my apologies, this is not a complete exhaustive list, but I just picked a few here to give some examples of what we were talking about. You will see there, if we start on the left, European projects. A lot of those are related to offshore wind, bringing power back from the North Sea to Central Europe. Weidmann have been heavily involved in those. Some early adopters, India, Brazil, Africa. There are several projects in those regions that are already active. And of course, across with our colleagues in Asia, China, and Lie is very familiar with many of these Asia Pacific projects. China is one of the leaders today with the largest ultra high voltage DC network. crossing the country, great distances, and he will share some of his experience there a little later. So that gives you an idea of some of the projects that we at Weidmann have typically been involved in to date. Next slide, please, Deanna. So with that said, what are the challenges that are driving all these inquiries for HVDC discussions? So we talk here that they're typically environments where conventional AC solutions are not as practical or don't address the application as well. I mentioned a couple already, but I will give you 4 examples here before I let our team talk about how we address those. So the first is offshore wind expansion. And of course, offshore wind today, where I'm sitting in the Rhode Island office of Weidmann, we have a current project off the coast of Massachusetts here with wind generation, and it's moving further and further offshore. Past Martha's Vineyard, for those who know the region. So as it goes further and further offshore, we're seeing long submarine cable distances where AC is just not practical, typically due to losses, which makes HVDC really the only possibility for these long underground submarine cables. And as I mentioned, that's a lot of the projects that we're currently working on in Europe. And that links nicely to remote renewable generation. So that's another topic. We see large wind, but solar, hydro resources in Asia Pacific region that are typically not located close to the big industrial energy consumers. So there's a requirement to deliver the power with minimal losses over large distances from those remote generation sites to large hungry power users across countries. And then moving on to the last couple of examples. So we talked about interconnecting power systems. So this is interconnections with different networks crossing different regional boundaries, countries. In Europe, we see this, where they want to basically have a system that can manage the exchange of power while still maintaining independent grid operations. And HVDC can control power flow and support generation of reactive power. And as Peter Heinzig educated me on a little bit earlier this month, then you can connect asynchronous AC systems. And that's a whole topic that I won't try to explain now. And finally, emerging load growth. So I think we're all aware of ongoing electrification projects, manufacturing expansion, large data center developments across the world right now that is creating concentrated demand growth. I also read an interesting article last week where there's also an issue with existing manufacturing facilities where, for example, they're implementing robotic forklift trucks and robotic picking devices for selecting products from a factory. And they're seeing a significant load increase even from those factories because, of course, when they replace with humans or forklifts that were formerly running on propane gas, now all of these devices require charging overnight. So there's a lot going on in the electrification space that is also just driving demand for additional large blocks of power to be delivered. And of course, I did make a note there. We hear a lot about data centers running higher voltage DC racks in their data centers. We're not talking about that specifically, but rather that utilities need to address transmission corridors. They have many requests for data center connections, and with that, they need to be able to deliver large amounts of power, often from those distant generation sources. And many of these areas where data centers are being developed is not necessarily the traditional center of loads, let's say, or high demand areas. So they have to address that. So with that short introduction, I will just explain what do we see that meaning for the transformer industry. So as I mentioned, HVDC is more than likely selected when power has to be moved over long distances or through transmission environments such as the submarine cables where AC solutions are not possible or at least less practical. And that has an impact on different parts of our industry. So from OEMs, we have a lot of customers who are exploring for the first time going into HVDC transformer projects and design. And utilities, of course. So they come to us asking what our experience is in evaluating future transmission options and increasing interaction with HVDC infrastructure. And finally, from an industry perspective, it's about knowledge sharing. There is a significant amount of knowledge out there that exists on designing for HVDC. But I believe that as more and more people, companies, countries start to look at HVDC, it will be critical that we share that knowledge, even if it is remaining a somewhat specialized application. So with all that said, I would like to hand over. So we will start with looking at bushing test arrangement design, and I will hand over to Lie. So Lie, we hope that your connection stays with us, and yeah, thank you very much. And I will join you all at the end for the questions and answers. Thank you very much, Lie. Over to you.
Thank you, Francis, for the introduction. Apparently, there is still some internet delay because I'm still on page 7. But anyway, welcome again from my side. I'm Lie Xiao, AP Design Manager. Have been working with Weidmann for more than a decade. I have been deeply involved in HVDC projects. The voltage level is up to plus minus 800 kV DC and be involved in the whole cycle from design, manufacturing, FAT, and on-site assembly. So let's discuss more details of the HVDC. Yeah, let's go to page 10. So, okay, so for AC and DC, from the power system point of view, the fundamental distinction lies in the time variance of the waveform because AC continuously cycle its magnitude and the reverse direction. So we have this 50 and 60 hertz, while DC maintains a constant and unidirection flow of the current. The fundamental distinction between AC and DC for the transformer insulation design lies in the material properties, which dictates the field stress. Because for AC steady state, the electrical field distribution is capacitive, which is governed by the permittivity, so also called dielectrical constant. So from the picture, we have this permittivity of the oil as normally as 2.2 and cellulose press board as 4.4. So it's end up the typical ratio of 2 to 1. And so more field is distributed inside the oil. While the DC situation is resistive, that it is dictated by the conductivity of the material. So we can see the ratio of the conductivity from oil to pressboard is 100 to 1 traditionally. So that means the field stress shifts away from the oil and concentrate within the pressboard and the barriers. So next page, please. Conductivity is not a constant, and it has a nonlinear function of the temperature and also the field. So here compares the influence between a different conductivity ratio for the field distribution. So you can see on the left side that if the ratio is 100 to 1, that more fields are concentrated inside the board. Next page, please. So here, this is regarding to the DC field plot of the lead exit under polarity reverse. So we need to be aware that under the normal steady state, that it is the field distribution is governed by the conductivity. So the insulation material, meaning the papers or the barriers or the press board, take the most voltages. So we are talking about the polarity reverse. So for the instant for the polarity flips, the voltage reverse, but the material don't react instantly. So the field distribution is still suddenly governed by the permittivity, so that the stress will rush into the oil ducts because oil has a lower permittivity, and so that it ends up a ratio of 2 against the press board. Knowing the conductivity and the permittivity between the oil and the insulation material, we can compute or calculate electrical field immediately before and after the polarity reversal. Next page, please. So development, from development to production to transportation and assembly, this is like a cycle of this HVDC, BTA, and lead exit. And to develop the HVDC bushing test arrangement, it includes the demand analysis, the structure and installation design, simulation optimization, and if the bushing test arrangement, which we call BTA, passed the test, then it means the insulation structure is verified, and we can apply this structure into the later on HVDC lead exit design. Otherwise, it needs improvement and adjustment. Next page, please. So now we are talking about bushing. Bushing is a core equipment of the DC transformer because it integrates the electrical connection, mechanical support, and so on. And it needs to go through various type tests, routine tests, like AC withstand, light impulse, switch impulse, and DC withstand, and polarity reverse. So it acts like a joint between the DC transmission line and the converter transformer or the HVDC transformer. So the bushing needs to guide the high voltage conductor through the equipment. And for the bushing test voltage, normally it's 10% to 20% higher than the transformer test voltage. And we used the bushing test arrangement, BTA, to verify the bushing and define the lead exit design methodology. Next page, please. So referring to the DC bushing standard, here we have this IEC and IEEE 65700, because if you need to talk about the bushing and also the bushing test arrangement, need to go through the details and to understand the request of the DC bushing for various aspects. Because here it's quote that the DC test on converter transformer and reactor bushing should be carried out with external insulation barriers and grounding planes surround the lower end of the bushing in the position as similar as possible to that of the intended service condition. So meaning that the design of the bushing test arrangement has a certain requirement, it should be fulfilled. And for the bottom half, we have this semi-sphere design. This is very typical for bushing test arrangement. And also during the design of the BTA, I need to consider the mechanical support structure inside the turret and make sure that the test voltage can be verified properly. Next page, please. So here has the list of the input data which needs for the bushing BTA design. Because first we need this bushing specification, and we need also the internal construction, especially position of the condenser layers, because it will affect the later on the field distribution, and also different test voltages, turret arrangement, size, height, diameter, and so on. And also additionally, depends on the bushing spec, that the relative position of the bushing towards the electrode, also the internal connections, and the base layer, and also the barrier system need to be considered during the design of the bushing test arrangement. Next page, please. So here there were three different plots, which is for the HVDC steady state calculation. The left one is the AC case, which the permittivity is dominant, and you can see that the bigger portion of the field is inside the oil. This is because of the ratio on the permittivity. In the middle is the DC case, that the conductivity of the material is driving the design. And in this case, the field is concentrated inside the material. And on the right side is the polarity reverse. And it can be described as a superimposition between the AC and DC case, because it occurs when switching the polarity of the DC grid. And the polarity reverse is necessary when the DC connection between the grids, because some grids need the energy flow in one direction, and after a certain time they change into another directions. And the field distribution in the polarity reverse is something in between the AC and DC, because it depends on the property of the material. The field stress in the material is higher than AC, but also stress in oil is higher than in DC. So design in the polarity reverse is quite challenging, and also need to consider the creep situation because of the equal potential line distribution. Next page, please. Here we have another example, is that to compare two different type of the DC bushing, and fit into the same bushing test arrangement, and they are operate under AC, DC, and polarity reverse status. And it can be seen that the equipotential line distribution are different under different circumstance. Next page, please. So just now we were talking about the steady states. Now let's focus on the transient situation, because for HVDC transformer, they need to withstand or go through this DC 2 hours test, and also the polarity reverse test. So for the DC test, you can see that at the very beginning, because of the capacitive behavior of the system, at the very beginning it looks like AC. but gradually after 2 hours is assumed as a DC. This depends on the conductivity of the components. And for the polarity reverse, it means that the system is tested under negative polarity for the first 19 minutes, and then positive polarity for the 90 minutes. Then again have this reverse, which is 45 minutes of the negative polarity. Switching is done within minutes. That's between two different voltage polarities, and this is very challenging for the design because of the transient behavior. So here you can see that we capture the plots under different time to find whether there are some critical areas or regions in the design under different time. Next page, please. So here is a comparison between the for the different voltage level and of the BTA. Here you can see the complexity of the BTA, and the weight and the height are increased, and it's a nonlinear design between each other because the weight and the height increase enormously, and the higher the voltage, the more complex of the design you would have. Next page, please. So talking about the HVDC projects here, that we have two kinds of design and, or the projects that the first is the design that we request the specification, and we have this projects that to understand the needs and the scope, and the goal and delivery time, and start this bushing test arrangement development or design stage, and then produce and transport. But also we have this IDA, which means insulation dielectrical analysis. This is a design review that we define the scope of the IDA, and we receiving the 2D and 3D modeling, define the material properties, and agreement on the voltage levels and the boundary conditions, and start the IDFM calculation and reporting. So that's the steps for the bushing test arrangement, calculation or design or review. And then we will step into the HVDC lead exit design, which is the part of my colleagues, Diana.
Great, thank you, Leah. Yes, so now we will mostly focus on the lead exit design philosophy, but also the production challenges we face for DC projects. Just a connection between Leah's presentation. So as Leah mentioned, the first step into designing lead exit for DC purpose, we have to have the input data from the bushing test arrangement, because the design used for the connection on the bushing is then the same one used in the lead exit. So after this has been established and designed, the next step is to check the needs for connecting the lead exit to the winding of the transformers, and the arrangement within the tank, and all the needed requests. But just to make a step back, when designing and producing such a lead exit, one has to know that there's a harmony between machine-produced elements, which require detailed executions and are state of the art, one would say. Then we have components which you can see have a variety of shapes and dimensions, and those are mostly produced by hand molding formed, and one has to be aware that for producing such highly complex product, you have to have custom-made tools, and this is mostly then one of the mostly time impacted element when producing a lead exit. And then at the end, we have the final assembly, which means to combine all this variety of elements into a final lead exit, which for DC has very narrow tolerances, sometimes even zero, and it is then very hard and very complex to execute. But to show that the design of such lead exits didn't just come out from nowhere, it is worth to mention that we have a legacy of producing AC lead exits. Those starting in two types. So for a modular lead exit produced for 2 voltage levels, here shown 420 and 550 kV systems. And the beauty in them is that we managed to produce them in a variety of length, height, angle, and mostly anything what the customer would require. Of course, there are some by the book, cookbook, and the others by custom made, but most of them are covered in previous designs. And then if we step a voltage level higher, then we have so-called W800 and W1000 lead exits, with logically then even more barrier systems. As we go higher to the voltage, we grow again in the width and height and in the in the dimension of the entire lead exit. So taking all this into account, one could say that we established well the AC lead exit production, and it was then at the end also a verification under electrical and mechanical tests. So passing all that led then to the situation that we are able to produce a much more complex lead exit for DC systems. Here, an important aspect plays those modular elements, because the lead exit for HVDC can be a 3-phase, and then we have a variety of shapes and interconnections needed, and some of them, like shown here, the interwinding connection element, are well established and designed in current usage. So now we switch to DC. For AC, we had the so-called AC lead exit family. For DC, it is not the case. As Leah shows it, the variations in the voltages is not linear. So like we had for the AC, just by increasing the barrier, the numbers of barriers. Here, it is mostly customized together with the manufacturer of the transformer. Also, when we do the insulation dielectric analysis and verifications for a BTA, there is this voltages from the bushing, which Leah mentioned are 20% higher. But for the lead exit, we focus on the voltages designed for the transformer. So this is the distinguishment in the voltage class calculation. And then, of course, here we have the variety, whether how many phases the lead exit covers and the insulation type. In order to produce such huge components, there has to be some investment in the production. Here shown some of ours. So we grow in length and general dimensions, and it leads to the need of, for example, a bigger oven. Then what is very common for DC lead exits are the so-called the barrier packages, and we will see them later. But they're huge and very heavy, so one has to invest in assembly systems for such barriers, heavy barriers, and then the shapes of the lead exits are not always that easy. So additional tooling when producing metal components is mandatory and very interesting. And here we have examples like Leah showed for the BTAs for some lead exits. We can't say that this is the standard design for 800 kV HVDC, so this is just an example. But here we can see those barrier packages, which are very familiar to DC for this attracting of the DC field in order to reduce the stress on the base layers. And of course, here we can see that they're on first glance very similar to AC lead exits as shown before. So when producing such lead exits and doing a final assembly test, one has to be aware of the size, that they're very heavy, and that there is a need of the crane operations. The tolerances are very narrow, and tools like guiding sticks and for tough tightened barriers is mandatory in order everything to fit perfectly together. And as you can see here, there's always some bends and elbows and needed joints for final connection. Those joints are actually are always taken into a big consideration because they present this connection between different components and sections of a lead exit. They're part of the cable connection from the winding and so, and they must be easily manipulated and rotatable in all three axles. Therefore, it is always necessary to do a check in terms of electrical and mechanical analysis. Here's just an example. So for this electrical analysis, it is recommended to do DC, and if it is the case, the polarity reversal steady state study of the joint in all three positions of the tolerance, because as we can see from those two examples we have of the field plot, shaded plot of the stress evaluation under DC, there is a huge variety depending on the final position of the joint. And as mentioned, this is done under voltage conditions of the transformers, not on the bushing. And to conclude, so the HVDC lead exits are very similar at first glance to the AC lead exits, but their complexity is much higher due to a huge amount of layers of barriers and insulation compared to AC, narrow tolerances, and there is for now no final cookbook depending, for example, on voltage levels, how a DC lead exit should be produced, but it is always customized and in agreement with the transformer producer, depending on their needs. And here again, so we see that the transformer board plays a big role in terms of, since the main field stress is attracted to it, so it is very important for the DC and polarity reversal impact. And just quickly, beside for example, the electric analysis Weidmann performs, shown by Lie in this presentation, there is also a need to have a look at for a DC project to perform a design review in the early stage. Of course, then a design verification with performing various calculations, 2D, 3D, in terms of polarity reversal and DC voltage conditions, and transient. Due to huge impact of the tolerances, manufacturing inspections is also crucial, and at the end, of course, FAT witnessing of the transformer is also something being a part of our engineering service. And if needed, in case of a failure or a damage case, we are also happy to jump in for a failure investigation and a root cause analysis. Yeah. Francis?
Yes, thank you very much, Deanna and Lie, for that presentation. We've had quite a few questions coming in. I guess we also had quite a few questions in advance. So to be fair to those guys who prepared in advance when they registered, I will jump to those, and then to all you who are asking live questions, I will try to get to you. So first question, and I think based on the presentation, Deanna, you could probably answer this one. So the question is, do the basic drying and impregnation requirements for HVDC applications with mineral insulating oil exceed, or are they the same as those for HVAC? So it's a question about the basic drying and impregnation requirements for HVDC. Are they same as HVAC?
So for HVDC, we can say that drying and impregnation is more advanced than for HVAC systems, because as we saw from the presentations, the impact of the transformer board is huge here, and therefore the moisture level has to be very low, because it can generate space charges on the interface of DC elements, and also particles floating in the oil can create possible difficulties, and therefore we recommend using additional filtering of the transformer oil for DC HVDC applications. Yeah, so those two aspects are the.
Okay, thank you, Deanna. And you mentioned in there, I'm going to jump around a bit here because with the questions you mentioned space charge in that topic. So let's get that one out the way. During Leah, maybe you can help because you were showing some very technical drawings there that you've tried to explain to me before. So during DC calculation, Leah, how do you handle the impact of space charge? Because we mentioned that there. Can you answer that one?
Yeah, thank you. That's a good question because Weidmann is aware of this phenomenon, and we have started the exploration of this topic many years ago. So we have considered this situation, but properly to consider the space charge during the daily work for the design of the HVDC means that you need both the accurate description of the material and also the advanced software or simulation. These are necessary, and this will include the description of the ion mobilities and also consider the insulating fluids and also the insulation structure and the calculation software. So above that, we consider that to consider the space charge is as more as an academic approach than the engineering approach. So for Weidmann, we have designed the HVDC insulation structure for decades successfully and using the classic methodology supported by the numerical simulation. So these are how we consider the impact of the space charge.
Okay, thank you very much, Lee. And while I have you, Lee, I'm going to address a couple of live questions just while we're here. Very quick ones. Somebody asked the field stress that you showed, is that calculated considering mineral oil, or which oil were you considering?
Here is considered as mineral oil.
Okay, thank you. And the other question that somebody asked, and I think it's covered in one of my overview slides from the start with some voltages there, but somebody asked if we've designed systems, which voltages have we designed for? Can you give me a top end and lower end?
We have designed different voltage levels, 200, 400, 600, 800, 1000 kV DC. So different voltage levels we have been involved in.
Perfect.
And delivered around the world.
Yep. Okay, we'll keep going because we have a lot of questions coming in, but I'll go back to one of the pre-questions, and Deanna, I'm going to put you on the spot here. Somebody's asked, and the question was, will we show an example, but maybe you can touch on this. Are electric field intensity values along field lines sorted and then cumulative average applied and compared to strength curves? I hope you understand that question better than I do.
Yes, yeah, we missed actually those post-processing, I would say, parts in these presentations, Leah and me both. So we only showed the shaded plots under a variety of voltage conditions. But yes, we have our internals rules which are used. But just to, since we are touching this post-processing, so for the AC, under AC voltage conditions, we use so-called field lines with strengthening curves, Weidmann curves. We evaluate point stresses, and creep lines, so the creep conditions. And the creep conditions is also evaluated for the DC and polarity reversal. But as we saw the huge impact and that the stress is transferred from the oil inside of the material, we evaluate also the stress in solid, meaning the stress inside of the material for DC and polarity reversal conditions, and with the impact of what type of material we are dealing it, and like Leah mentioned, the variety in the conductivity and permittivity, and using, of course, then internal rules to evaluate whether the stress in the solid is acceptable. Yeah.
Okay, thank you. And Leah, and this question that came in, I'm just going to take one more from the pre-questions and then jump across because we have around 4 minutes left. So I know the question here, you may take a long time to answer, so maybe you can answer it as short as possible. But how does the insulation structure vary in HVDC in comparison to HVAC? And specifically, does insulation thickness matter? But as fast as you can, please.
Okay, so here if we compare between HVAC and HVDC, so if we look at the properties of the material, for HVAC design of the insulation, it's more straightforward because we have this permittivity value, which is quite stable. And for the HVDC design, it's for the conductivity, it is not a constant. It will be affected by the temperature, the local stress, and so on. So for the DC condition or the DC designs, normally more complex, and under the DC condition, a thicker solid insulation needs to withstand the field stress, and this determined how the field distribute between the oil and the solid, and drawing the polarity reverse because a thicker insulation will accumulate more charges, which will increase the stress locally. So, but it's also essential that the insulation needs to withstand the stress. And moreover is that for the thick insulation material has the lower thermal conductivity. So because we know that the conductivity is also greatly influenced by the temperature. So this will potentially increase the local temperature, and in which that will shift the conductivity ratio and the impact on the field between the oil and the press board. So in short, the fundamental difference in HVAC and HVDC is that you can not simply scale from HVAC experience. The HVDC design is much more complicated because it's conductivity driven, and you need to think about the space charge, polarity reverse, and there were also quite some design constraints behind it, so that you need to find the optimized design between different aspects. I hope it's short enough.
Almost, but let's jump very quickly to a few live questions, and we will review these afterwards and try and get back to as many of you as possible. Quick hello to all of us, but especially to Deanna from Michael from National Grid. The question he had is, are transformer OEMs approaching Weidmann to carry out the transformer lead exit design for converter transformers, or do we license these designs to transformer OEMs? A very quick answer is fine.
So we actually mostly do the verification of lead exits and help improvement of previous established lead exits from the customer. So in terms of design, yes, we have some prepared from experience, but the customer is actually then providing his initial needs, and based on that, it is then being grown.
Okay.
The final design. And hi, Mike.
Thank you. And one question that I found interesting, you mentioned zero tolerance, Leah, and Deanna, you also touched on how critical tolerances are, but you never gave us any numbers. How do you define zero tolerance for lead components? Very, very briefly.
So when we look at the barrier system of a final lead exit design, one would say that it is made out of one block of transformer board, but actually it consists of a variety of number of barriers stuck together, and they have to have this perfectly fit, like they're acting as one component together. But it can't be, because we have to have a certain oil flow and due to heating of the transformer. So yes, the tolerance in some cases is 0. So it has to be a perfect fit. And as we show for the joints, there is this huge impact just in few millimeters positioning of a joint, how the field will behave. So counting that up, if we would not take it into account in their tile lead exit, it would not end up well. So yeah, every millimeter, I would say, counts in those designs.
Okay, thank you, Diana. I'm going to ask one more question. Normally we wrap up now, but very quickly, does insulating liquid in HVDC transformers age differently than AC transformer, than in an AC transformer? Do we have any evidence of that or data? Maybe it was the wrong final question.
No, because it depends on the. So for DC, even the initial oil quality depends. So using one oil type or one oil quality for the FAT and not applying it with characteristics for the calculations, and then at the final running and putting the transformer in production into the field has a huge impact. So yes, the oil is definitely has a huge impact. And then of course during time the oil changes, also for the AC transformers, but for the DC, yeah, I would say it has then a bigger impact in aging and the influence on the transformer.
Mm-hmm. And I would, sorry, I just want to add one more point, is that because you also need to consider the operation conditions, because for HVDC transformers, they are operating full power most of the time. But for AC transformer, for a lot of cases, they are operating maybe 20 to 30% or 50%. So the loading in the transformer is different, meaning that the temperature inside your transformer is different. So you need to compare under a similar situation that they are full power to design to the thermal limit. Then you can compare the aging topic. So because the temperature will be a big factor to impact the aging. So yeah, that's the difference here.
Okay, thank you very much. With that, I appreciate you all staying with us for the full hour. I see some of you are dropping off. I know you have other meetings or you're going home if you're in certain parts of the world. So thank you very much to Deanna. Thank you very much to Leah. And thank you all for being with us today. I hope that you, if you're in the Northern Hemisphere, enjoyed the summer. If for those in Europe, we will be at Seagrey in Paris, the session's there in August. So I do hope you drop by and say hello to us there. And I wish you all a good continuation of your day. Thank you very much for being with us. we will be back later in the year with another webinar. Thank you, Deanna. Thank you, Leah. And
You're
take
welcome.
care. We'll see you all soon. Thanks.
Bye.
Thank
All.
you.